All right, so let us now try to find out what is the rotational partition function. So just like before, we'll just write the rotational partition function as sum of our states or sum over levels, but in this case actually we'll use the sum over level notation, because the rotational energy levels are so say for example, if I have a rotational energy, usually the quantum number we denote as J, and that we write as H C B tilde J into J plus 1. And this B tilde is called the rotational constant. The way we have written it is that B tilde is expressed in units of wave numbers. So that's why Hc into wave number unit is basically the energy unit. Now for any state with a J quantum number, we have the energy levels are 2J plus 1 fold degenerate. So we can just use the other formula. It's the same formula, but just we just have to make sure that we are taking the sum over levels. E to the power minus beta epsilon j. This is capital J, and then you can just write the numbers, and that will be nothing but 2j plus 1. So I'm summing over j now because I've changed the index, and e to the power minus it will be beta hc b tilde into j plus 1. Now you see that we can actually write this thing again like before, as an integration, because we know that the rotational energy levels compared to at room temperature behave like a more or less continuous energy levels. So the quantum number goes from 0 to infinity in this case, and I have 2j plus 1 e to the power minus beta hc b tilde j into j plus 1. Now if you have something like say e to the power minus the entire constant, I'm writing it as say a into j plus 1, and if I take the differential, so how that what it will be? So it will be basically e to the power minus a into f of x, something like that, differential of that. So it will be minus a e to the power a f of x into differential of that f of x. Together what we will get is minus a. Now j into j plus 1 is j square plus j. If I take the derivative, it will be nothing but 2j plus 1 into the e to the power minus a j into j plus 1. So you see that we can actually make use of that fact and write the entire thing as a differential of e to the power minus beta hc b tilde j into j plus 1. But then we have to an extra constant minus a, so we have to divide by that. So we have to divide by minus of beta hc b tilde, and then this integral. Now this is a very straightforward integral. Now it's integral of dx, so the value is x. So I have to just evaluate e to the power minus beta hc b tilde into j plus 1 between the limits j is 0 to z equal to infinity, and I have one more constant in the front, beta hc b tilde. So the upper limit in this case, e to the power minus infinity, it is 0, and the lower limit is 1, e to the power 0 is 1, so it is 0 minus 1. So together it will be minus 1, and now you have a minus sign here. So it will be 1 over beta hc b tilde, and we can actually write the value of beta. You can actually look up beta is 1 over kbt, the b tilde values, and it will be, I'm just writing here the final expression, 8 pi square I kbt divided by h square. Now I is moment of inertia, which is mu r0 square, where r0 is the equilibrium bond. And suppose I am talking about a diatomic molecule which vibrates. So if we think that it doesn't vibrate, it is rigid in the sense that I'm only considering the equilibrium bond length, as if the bond length is fixed and then it is rotating, then we can think say that to be r0. So this is the expression for rotational partition function. Now we have to be careful for homonuclear diatomic systems, or systems which have symmetry. For example, let's say if I take carbon dioxide, or another homonuclear diatomic molecule like say hydrogen. So what will happen, you can see that even an 180-degree rotation will create a similar structure. So for that we always introduce in an ad hoc fashion here a number sigma, which is known as the symmetry number. So it just makes sure that we do not overestimate the number of rotational states. So in this case CO2 or H2, since it's a linear molecule, the symmetry number will be 2, but it can be it can take some other numbers. Now there is a reason for origin of this symmetry number, and we'll briefly discuss that, what is the reason of the origin of the symmetry number. And all of you know about that normal hydrogen molecule has two nuclear isotopes. One is called the orthohydrogen and the other one is called the parahydrogen. Now what are ortho and parahydrogens? Now you can think that, okay, fine, I have two hydrogen nuclei and of course two electrons, and these nuclei can actually have, so it is basically proton, and protons are fermion. So I have actually two spin half particles. Now depending on their arrangement, I can have both spins up, both spins down, one spin up, one spin down, and it can be on two ways. This spin can be down and this spin can be up. Now again the protons are being fermions. These are basically indistinguishable particles, and then so according to Pauli's exclusion principle, you can actually have total there are 4 combinations, so you'll get basically total 4 states. And what are those 4 states? You will get you can see that after interchange of any two nuclei, if the total wave function is not the total wave function. First let us focus on the spin part. So if we let's say if I just call this as the alpha spin as the up spin and beta spin as the down spin, then you can easily figure out that if I have nuclei 1 in alpha state and nuclei 2 in beta state, if I just change these two numbers 1 and 2, it doesn't change the total spin part of the wave function. But if I have something like alpha and beta, so this kind of combination, so then I have a problem, because nuclei are indistinguishable. So you cannot say which one is up spin and which one is down spin. So in order for that, what we do is that we take the symmetric combination as well as the antisymmetric combination. So alpha 2 beta 1 and also the minus combination. And similarly here for this thing we will have beta 1 beta 2. Now this combination as well as the symmetric combination, these three actually forms a symmetric spin wave function, spin part of the wave function, and then the minus combination gives you the antisymmetric spin combination. Now since protons are also fermion, so the total wave function has to be basically antisymmetric. So the symmetric spin part goes to the antisymmetric space part, and in this case actually it will be antisymmetric rotational part. So basically we are talking about the symmetric part of the spin and antisymmetric part of the spin, and the antisymmetric part, if we have the antisymmetric part of the spin, it will go with the symmetric part of the psi rotation. So we can actually use a slightly different rotation. and we could write it as symmetric psi spin, antisymmetric psi spin, something like that. Now this antisymmetric psi spin is actually related to the odd j values, and the symmetric is related to the even j values. Now you see that for every if I write the total wave function, or in this case let us suppose that if I write we're talking in terms of the partition functions, the partition function, which is the sum over 2j plus 1 into e to the power minus beta epsilon j, and sum is taken over all j. Now I can actually divide this sum into two parts. One is basically I can sum over odd j's, plus I can also sum over even j's into 2j plus 1 e to the power minus beta epsilon j. And then you see that all these even j's, which are basically associated with the symmetric psi rotation, but the antisymmetric spin part, the statistical weightage for that will be 1/4 only. And for this actually you will have a 3/4 statistical weightage, because you have the symmetric spin part, you will get three types of combination, because it is alpha alpha, beta beta, and a symmetric combination of alpha beta, like alpha beta plus beta alpha. So thus we see that these wave functions, or this partition function, corresponds to the it is the orthohydrogen, and which are basically sum over the odd rotational function, and this corresponds to the even functions, which are basically known as parahydrogen. So that's why at room temperature, statistically, if you measure, you will get always 3/4 of orthohydrogen isotopes and 1/4 of the parahydrogen isotopes. And this is the origin of this rotational number. So that's how it basically comes, and you have to be very careful when you calculate these rotational partition function, and that's how the symmetry number appears. So the origin of symmetry number is very much quantum mechanical in nature. It comes from the Pauli exclusion principle for fermions. Now for our most of the discussion, we will not use the symmetry number too much until and unless we encounter a problem where actually we have something like a homonuclear diatomic system for which this symmetry number is required. Now let us talk about the vibrational partition function, and again, so the Q vibration is nothing but sum over e to the power minus beta epsilon vibration. Now we know that epsilon vibration is nothing but we have V plus half. V is the quantum number, and for vibration we have a 0 point energy level, and we can write it as h bar omega, you can write it as h nu, whichever way you prefer, and the sum is taken over V. But in this case actually I am not replacing the sum by integration. The reason, as we said, that even at room temperature, for a vibration something like few thousands of wave number, you will see that predominantly the ground vibrational state is populated. So it's basically a discrete energy levels or few energy levels that are populated, and energy levels are not continuous compared to your KBT or 1 over beta. So we'll just use the sum as it is. Now this half, what will be the partition functions? Like if I take the V, and so it's a sum, so let us just calculate the sum like this. So I'm taking the sum over V. V is going from 0 to 0, 1 to something like that. So the first one will be e to the power minus beta half h nu. The second one will be e to the power minus, now you can see it is 1 plus half. I'm just writing it as 1 plus half in that way, not 3 by 2 h nu. The third one will be e to the power minus beta, it will be 2 plus half h nu. So that way we'll have the sum 3 plus half h nu. So what we can do, that half h nu term we can take common, and then inside bracket I'll have 1 plus. Now here for this term, for the second term, let us look at it. It will be to the power minus beta h nu. Let me just write it like this. The third term, it will be a minus beta 2 h nu. So that term I'm writing it as e to the power minus beta h nu squared. And then similarly the fourth term I'm writing as e to the power minus beta h nu cubed. We should use different brackets here. And then what we figure out here is that this is nothing but the series 1 plus x square plus x cube, this series, and the value of the series is 1 over 1 minus x, where x in this case is e to the power minus beta h nu. So we can readily write it. It is beta h nu by 2 times 1 by 1 minus x, and that is e to the power minus beta h nu. So this is the vibrational partition function. Again, sometimes the vibrational partition function is measured from the 0-point vibration. So you basically subtract that and then calculate. In that case, you will see the expression for the vibrational partition function as 1 by e to the power minus 1 minus e to the power minus beta h nu. So we'll be using this expression when we'll be discussing the transition state theory. Now let us now look at, so we have so far discussed what are the values of the partition function or the molecular partition function. We talked about the translational part, so which is this. We talked about the rotational partition function, which is this, and then we talked about the vibrational partition function. And electronic partition function usually will take to be 1, because the definition of partition function is per minus beta epsilon I, but we say that it's only the ground electronic set that is populated, and that epsilon I, let us just write it. So what I'm saying here, Q electronic, that we say that it is only one state, so it's sum over all the electronic energy levels e to the power minus beta epsilon I, but it is just only the first energy level, so beta epsilon 1, the ground state. And this ground state energy, if we take it to be 0, because it's just a choice of 0, so then actually it becomes e to the power minus beta into 0, so that becomes 1. So until and unless the electronic ground state is degenerate, or something like, say for radicals, say I have an unpaired electron, so then I'll have a doublet state in the ground state. In those cases, the partition function will be 2. So because you can think that then I have basically a degeneracy of 2, and that degeneracy gets multiplied, but the other part is same. So what we just learned is that okay, so what will be the total energy of the molecule? Now, as we talked about the translational case, if we have some energy, let's say we gave you a particular example that if we have a total energy, something like say 6 n square, this example, 6 h square by 8 ml square, so that's the energy level. But then we found that this is actually composed of 3 energy states. And then how we got it? Because actually you know that the translational partition function that in 3D is basically addition of the energies of the 1D, and that's why the energies are additive. That's why the partition function came as a multiplicative way, and that's why we got basically the q to the power 3 by 2 term, which we derived at some stage, this 3 by 2 term. Similarly, the total energy, suppose if I am saying that I have some energy level of the molecule I, but that I corresponds to some translational energy, some rotation, some specific translational energy, some specific rotation energy, some specific vibrational energy, which means actually this EI corresponds to some translational energy, some specific n, some rotational, sorry, we are writing the trans, rot, all these things in the as a superscript. So let us follow this notation, and the quantum number j, and some vibrational partition function, and some electronic partition function, of course. And let us denote for electronic quantum number, let us just say it is not I, we have already used I here. Let's say we call it as some m. So what we are saying here is that then in a similar token that we know that Q total is basically sum over all these energy levels with all their degeneracies. If I am taking this sum over levels, a to the power minus beta epsilon I, but then you can actually write the epsilon I in terms of the translational, rotational, and vibrational. Then you'll easily figure out, and you write that e to the power a plus b plus c is actually e to the power a times e to the power b times e to the power c, that way. So then you can easily figure out that you have, or you can actually use the state level here, because we're just talking about the states right now, and then we can convert it into levels. So I have sum over I, which is taken over states, and then I'm writing e to the power minus beta. Instead of epsilon I, I'm writing epsilon n trans plus epsilon j rotation plus epsilon v vibration plus epsilon m electronic. So all these energy levels. Now we can actually write this thing in the next step as sum over states e to the power minus beta epsilon n trans times e to the power minus beta epsilon j rotational times vibrational times electronic, and then we can actually write separate these terms separately. So we write them separately, that we are taking sum over n first, which is basically the translational part. So let us write it explicitly into, then you'll write the rotational part, which is e to the power minus beta e j rotation. Sum is taken over the rotational quantum numbers, and again this is a state. Similarly for vibration, similarly for electronics. So you'll get at the end of the day, this is nothing but Q trans into Q rot into Q vibration into Q electronic. So all the partition functions will be multiplicative. Now this is an important result, which is a very straightforward result, but we'll be using it quite frequently. Now we have already discussed that, okay, so what is partition function? But now this partition function is a molecular partition function, and you can actually build up the macroscopic energies from that. Now how do you approach that problem? Suppose I ask you this question, that what is the internal energy per mole? Can I write it in terms of the partition function? The answer is of course yes, because if we can actually calculate what is the average energy per molecule has, then I can just simply multiply the average energy per molecule into the Avogadro number. So this average has to be first calculated. Now let us see what is this average. Now this average means again it's basically the total energy divided by the number of molecules, and total energy already we know the total energy's expression, it is nothing but Ni epsilon I, and remember the number of molecules expression was sum over Ni. Now Ni divided by the sum over Ni is the probability which we talked about. So this is nothing but, we have to take a summation here over I. Let us just keep this n as capital N only, and then what I am doing, watch carefully. So I have a sum over I, and then I am writing this n inside this summation. into epsilon I. Of course, n is nothing but sum over ni. And then what is this thing? This is the probability distribution, and that is nothing but e to the power minus beta epsilon I by sum over beta epsilon I, which is q. So q is nothing but the sum over e to the power minus beta epsilon I. And then I have this sum over I epsilon I. So I can take the q outside. So it will be epsilon I e to the power minus beta epsilon I. But then you look at this equation. If I take e to the power minus beta epsilon I and take the derivative with respect to, say, beta, then what I'll get is we'll have minus epsilon I e to the power minus beta epsilon I. So we have here right now the epsilon I e to the power minus beta epsilon I. So it will be a minus sign which is included. So I can write it as minus 1 over q sum over derivative with respect to beta of this quantity e to the power minus beta epsilon I. Now this derivative is with respect to beta. So this derivative as such doesn't depend on the summation. Differential operations are linear operations, so I can actually take it outside the summation, and I could just sum this quantity e to the power minus beta epsilon I, and that is nothing but q again. So this is nothing but minus 1 over q d beta of q. Now what is this quantity? 1 over q d beta q. This is nothing but if I take, say, ln q and then take the derivative with respect to that, so I'll have 1 over q, and sorry, if we have d beta, say, of 1 over q, so I'll have dq d beta. So this quantity is nothing but d ln q d beta. So as we see, the average energy per molecule is nothing but this. So now we can easily calculate the total energy or the energy per mole, and that's a macroscopic quantity. So if you know the molecular partition function, beta, of course you know this is a temperature derivative, it's 1 over kBT. So if I know this molecular partition function, I can actually calculate the macroscopic properties. And similarly, we can actually calculate many other properties like, say, entropy or the molar entropy. We can calculate the internal energy we have showed, and then we can calculate the Gibbs free energy. And once we calculate the Gibbs free energy, from that actually we can also calculate the equilibrium constant. Now suppose I have an equilibrium which is between some reactants is going into products, and then for that equilibrium I'm just writing the equilibrium constant as this. Now suppose there are some in a free energy diagram, I have suppose the reactants energy levels are here, the product energy levels are here. So what you can show, I'm not showing it, I'm not doing the derivation right now, so you can actually have a look at any standard physical chemistry textbooks which are referred to you. So in some sense you can think of the process going from, say, reactants to products as this. So you are going, you have a dissociation energy which dissociates the reactants. Suppose this is a continuum of energy, and similarly you could also think about the dissociation energy for the products. Now you can show that this and this is basically the Gibbs free energy change, and you can show going from reactant to product. If I write the equilibrium constant in terms of the reaction quotients which are related to the Gibbs free energy change, then you can show that finally if this energy difference, the Gibbs free energy difference, if we write it as say epsilon star or something like that, then we can write the equilibrium constants in terms of the partition functions of the product divided by the reactant times e to the power minus epsilon star. We are writing this notation, epsilon star by kBT. If we write a molar notation, so you should use, instead of kBT, you should write RT, but similarly you write as capital E for the molar notation. But whatever it is, there is a point to discuss here. First of all, you can have many reactants, but if I have suppose A and B are the reactants, suppose it's a bimolecular reaction giving you a product and which is in equilibrium with A and B. So then this reactant partition function is nothing but partition function of A times partition function of B, and that is obvious. Secondly, this is, although I have written it as a partition function, strictly speaking this is partition functions per unit volume. So the reason is, remember that what will be the partition function of A? It has translation, rotation and vibration, but translation always comes with partition function per unit volume, because if you remember that the translational partition function, let us go back here. So we had this Lx, Ly, Lz, which actually together gives you the volume of your macroscopic system, and that volume we always divide by the translational partition function. So the volume part always gets associated with translational partition function. It makes sense because the energy levels depends on the volume of the container, because in particularly in a box model it depends on the length of the container in 1D system. So similarly in a 3D system it depends on the volume of the container. So but rotation and vibration and electronic degrees of freedom, these are internal motion, they do not depend on the volume. So when you write this QA as say QA translation, QA rotation in that way, and QA vibration and QA electronic, so you associate this volume with the translation only, and then you calculate it. Similarly for QB also you have to do the similar thing. So that's how we calculate the equilibrium constant. One more point here to note, that this dissociation energy means this experimental dissociation energies. There are two kind of dissociation energies. Suppose I have a bond vibration and the bond is dissociating. So usually the energy levels, the potential for bond vibration is anharmonic potential. So there actually you have the 0 point energy, as we just discussed, just like harmonic oscillators, you have a 0 point energy. And then suppose you are measuring, if you measure the energy from the 0 potential, that energy you call it as D0, as opposed to the energy you have just drawn, which is the experimentally determined quantity, which you call as DE. So this DE actually already includes the 0 point effect, because you are not starting from your 0 of energy, but you are, if I call this level as your 0 of energy, of the total energy, so this is suppose the electronic 0 of energy, and then you have the vibrational manifold on top of it. On top of it, on the each vibrational manifold will also have, each vibrational level will also have a rotational manifold, and each rotational manifold will have translational manifold. That's how you describe the total energy of the system. And then you see here that you have a DE here. So these are all actually DE. So it is basically the difference of the 0 point energies of the reactant and the product. That is very important thing. So it's not that between the 0 difference, it's basically taking into account the 0 point energies always. Now we'll stop our discussion on the this part where we discussed briefly the statistical mechanics or statistical thermodynamics, again from a very basic point of view. We only talked about the molecular partition function. So what we learned in this lecture is that what we need to remember, which will be necessary, that we got a formula for 3D translational degree of freedom. Just writing the 3D version. So it is nothing but 2 pi m kBT divided by h square raised to the power 3/2 into volume, and then we have the rotational partition function, which is 8 pi square I kBt divided by h square, and then we have also the vibrational partition function, and that is 1 over 1 minus e to the power minus h nu by kBt. And remember that there could be many vibrations in the molecule, like there could be, so then you have to calculate the partition function for each degrees of freedom, because usually you have 3 rotations, and you have for a linear molecule you will have 2 rotational degrees of freedom. For a nonlinear molecule you will have 3 rotational degrees of freedom. So we'll ask you to figure it out in a problem set. What is this we have calculated, and how we can distinguish what will be the different rotational partition function, if there is any difference between 2D and versus rotational partition function for a 3, meaning if it is a linear molecule and if it's a nonlinear molecule, how the rotational partition function will change. And also remember that we introduced our symmetry number, and we said that for a diatomic molecule or for a symmetric molecule, linear symmetric molecule, we'll have to introduce this signal. Now one thing to you can easily figure out that this Q rotation must be for it's derived for actually linear molecule. The reason is you can see here, just look at the factor here. So it is basically 3 by 2 here. So I have in the denominator h bar squared. If it is a 2D problem, so then it will be basically 2 by 2. So I'll have h bar squared. So it readily tells you that it's not a 3D version. So you'll be asked to calculate the 3D rotational partition function, and then you have vibration. But vibration again, you'll have, suppose if my molecule or the system has, it's an n particle system, each molecule has suppose n atoms or something like that. So the degrees of freedom will be 3n. So then it will be 3 translation depending on the molecule, whether it is a linear or non-linear. By the way, this 3 is giving rise to this 3 by 2 factor. So I can have 2 degrees of freedom or 3 degrees of freedom. So we'll have 3n minus 5 or 3n minus 6 vibrational degrees of freedom. So each vibration will have a characteristic vibrational frequency nu, and so what I'm writing it is actually for a particular vibrational degrees of freedom. So if you have, suppose for example, 2 vibrations, so then this total vibrational partition function will be vibrational partition function for 1 vibration times the vibrational partition function for the second vibration. And the good thing with partition functions is that these are all multiplicative because the energy is additive. And electronic partition function, we usually said this is all equivalent to basically we can write it as the electronic degeneracy, because the other part is just 1. So it will be identical to the electronic degeneracy, which in most of the cases will be 1. And finally, we also talked a little bit about an expression for the equilibrium constant, where we wrote it as the equilibrium constant is nothing but can be expressed as the partition function of the reactants and the partition function divided by the partition function of the products times exponential minus E star by RT, where E star is the difference. Some textbook actually write it as delta E0. So the delta denotes it's a difference in energies, and 0 says that it is basically difference in the 0 point energies. So we'll conclude our discussion here, and we'll be using this all this expression heavily in when we calculating the rate constant for from the transition state theory, where we'll have this concept of an equilibrium between reactants and a transition state that will hypothesize that it exists briefly before the reactants are going into products, and we'll cleverly introduce the same concept there, and then we'll calculate the partition functions, and then we'll see how one can calculate a rate constant from the thermodynamic parameters, which are very time independent parameters, which is a very interesting theory. It is called transition state theory. We'll be talking about it in details later. All right, thank you.